Hello Year 12 chemists, welcome to TP's Chemistry Cuts. This clip shows a worked example of how to use percentage composition data to calculate an empirical formula. The empirical formula is then used along with mass spectrometry data to calculate a molecular formula.
Molecular formula tells you how many of each type of atom there is in a molecule of something. So this is applicable only to molecular substances, unlike an empirical formula which can be used with any type of substance. Now, generally, or often, not generally, often the molecular formula and the empirical formula will be the same for a molecular substance. Okay? But sometimes they are not. So often, so the first thing, of course, to say is this only for molecular substances. This for all types of substance. Now, if we're looking at molecular substances, these two can often be the same. They tend to be fairly simple, so let's give some examples. Water, that's the molecular formula, it's also the simplest ratio. Carbon dioxide, okay. Ethanol, etc. So there's a lot of them, it's not exceptional that this happens, but many, they're different. So if we look at a simple example, if we look at glucose, okay, what's the formula for glucose? So the molecular formula is C6H12O6, because that's telling you there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in one molecule of glucose. If we look at its empirical formula, however, what's the empirical formula? CH2O. Excellent. That tells us that for every carbon atom, there are 2 hydrogen atoms and 1 oxygen. So it's a different meaning. So we have to ask ourselves, when we've got an empirical formula, is that going to be the same as a molecular formula if we've got a molecular substance? Because we don't know straight away. Okay? So we need to be able to go to the next step and work out a molecular formula. So this is all basically taking us to the next bit. And don't assume that they're going to be different. They may not be. But we need to work out how we go from one to the other. Now this is a bit of a cop-out in that the actual method we use, you don't really come across until next year. We use something called mass spectrometry, which is part of the spectroscopy unit for next year. And the main purpose of mass spectrometry is it will tell you the molecular mass, or the molar mass of a substance. And that's as far as we need to go. So if you need a molar mass, okay, you get that from mass spectrometry. Now for a molecular substance, basically what you're finding out is the mass of the molecule, or a mole of those molecules. Okay? So it's not related to the empirical formula, it's a mass related to the molecular formula because of the way the technique works. Just accept it, don't let that confuse you. Next year you'll see how mass spectrometry works and why it gives you the mass of the molecular formula. So, what we're finding, what's the relationship between the empirical formula and the molecular formula here? That is actually 6 times the empirical formula. Okay? If we take a different example, let's have a look at a different example. If you look at ethane, okay, its empirical is equal to CH3. The molecular formula is C2H6. So if you want to go from that one to that one, it's times 6. What about from this one to that one? So it's times 2. The point I'm making is every time you go from an empirical formula to a molecular formula, you're multiplying by an integer number. It could be 2, 3, 4, whatever. So the molecular formula is always an integer times the empirical formula. So why don't we write that? And I'll just put it as times x. And we'll put where x can equal 1. That means that the molecular formula and the empirical formula are something like one of these, where they're the same. Or it can be 2 times, like with ethane. And it can be more than that, so 3 up to many, very large numbers. Okay? So if we take this formula here, sorry people, but we're going to do a little bit of algebra. Why don't I actually take the molecular formula and divide it by the empirical formula? So, molecular formula divided by empirical formula equals x, where x is an integer. Problem is the molecular formula is in terms of moles, isn't it? That's telling us 6 moles of carbon to 12 moles of hydrogen to 6 moles of oxygen. And it's the same with the empirical formula. In fact, the empirical formula we get from, as we'll see, as we've done, we get the empirical formula from percentage composition measurements. And that's telling us the ratio of moles of these things. What we need, what we've got for the molecular formula is the mass of the molecular formula. If we get the mass of the empirical formula and divide that into the mass of the molecular formula, you're going to get the same ratio, because the mass and the amount in moles are directly related by that m equals n, little m over big M. So whatever the ratio of moles is, the ratio of masses is the same. Okay? So instead of writing it like this, we can write it like this. The mass, or the molar mass of the molecular formula divided by the molar mass of the empirical formula is equal to the ratio between the two formulae. So if we can work that ratio out, we then go back to our empirical formula, which we've worked out from experimental measurement, multiply all the atoms along there by that ratio factor, and it will give us the molecular formula. It really is quite straightforward. Okay, so the thing you need to remember is this equation here. Now we're given the molar mass for the molecular formula. That's the value that comes from mass spectrometry. Okay? This we can calculate because we're going to use some percentage composition data to work out what the empirical formula is. Once we've got the empirical formula, we can work out its molar mass using atomic masses from the periodic table. And that's what we're going to do with the example on the board. Okay. So we're given this, which is here. What we've got to do is first of all use this data here to work out the empirical formula. Then we can work out the molar mass of that empirical formula, divide it into this value here, and we'll get an integer number. So then we can take that integer number, multiply the empirical formula by that, and that's what our molecular formula is. So it's a relatively straightforward procedure. As I say, once we've done it once, because often when you speak it through, it sounds a bit confusing because you've got two types of formula, and you convert into a mass, then back to a formula, and so on. It really is quite straightforward, as you'll see. So the first thing we have to do is we have to work out the empirical formula for quinine. We've got some percentage composition data. We can use that to work out the empirical formula. Okay, so that's the first step. So, what's the first step of the empirical formula calculation? Into grams. So, we're going to assume that we've got 100 grams of material. Assume 100G. And I'm just going to do it like a little table. And this is how I'd recommend you do it in the real thing. So we've got C, H, N, and O. Okay, so we're going to assume 100 grams, so we've got 71.4 grams of carbon, 7.41 grams of hydrogen.
74.1.
Sorry, 74.1 grams of carbon. 9.86 grams of nitrogen. I'm really losing, aren't I? 8.63 grams of nitrogen and 9.86 grams of oxygen. Now what do I do? So I divide by the atomic mass. Why am I doing that? Good. So convert to mole using n equals little m over big M, where big M is the atomic mass. So we've got 74.1 over 12.0. We've got 7.41 over 1.00. We've got 8.63 divided by 14.0 and 9.86 divided by 16.0. So first one, 6.18. But this one? 7.1. Oh yes. Genius here could have worked out on that. 8.63.
0.616. 0.62.
And this one?
Same. 0.62.
Okay. So what that's telling us then that the formula is C 6.18, H 7.41, N 0.62, O 0.62. But that's not very convenient. So what do we do? Divide by the smallest number, which is 0.62. So we've got 6.18 divided by 0.62, which is equal to 10 approximately. 7.41 divided by 0.62 is 0.62 divided by 0.62 is 1, and 0.62 divided by 0.62 is 1. So what this is telling us, and this is what you should do at the end, is the empirical formula is C10H12 then O. Okay? Now just a quick word about molecular formula. It's international standard practice that the usual way of writing a formula is C first, H next, and then everything else in alphabetical order. Okay, so if you're not sure about it, there's oddities like H2O and things like that. No, that's not H2O, but there are oddities. So particularly when you get to ionic compounds, everything seems to fall down. But with a molecular formula for an organic compound, this is the general standard way of writing it. C first, H next, then alphabetical order. Okay. So, what we need to do next to work out the molecular formula is use this formula. But we haven't got all the values yet. We've got the mass of the molecular formula from mass spectrometry, but we haven't got the mass of the empirical formula yet. So we need to work that out. So, empirical equals 10 times 12 plus 12 times 1 plus 1 times 14 plus 1 times 16. And I've done it in longhand, so you remember how you're doing this. You've got 10 times carbon's atomic mass, 12 times hydrogens, 1 times nitrogens, and 1 times oxygen. Somebody could quickly tell me that.
162.
162 grams per mole. And so M molecular divided by M empirical is 324 divided by 162, which is 2.
Yeah.
So molecular formula is C20H C20H24NO.
N2?
Oh, so N2O2?
Yeah.
Nice. So those are the two answers. If you get both of those right, that's excellent.